In this video, I'll give a quick refresher on linearly independent sets, and then we'll talk about bases for vector spaces. So let's remember that a set V1 through Vp of vectors is linearly independent if the equation x1v1 plus x2v2 summed up through xpvp equals the zero vector only has the trivial solution. Another way we can think about this is that a set of vectors is linearly independent if none of the vectors can be written as a linear combination of the others. To check if a set of vectors is linearly independent, we form the augmented matrix v1, v2 through vp augmented with the zero vector, row reduce it, and see if there are any free columns or variables. If all of the variables are basic variables, meaning all of the columns are pivot columns, then we know that the set is linearly independent. However, if we do have free variables, then the set is linearly dependent. So as we've seen from examples, subspaces are often written as a span of a set of vectors. For example, the column space of a matrix or the null space of a matrix is written as a span of vectors. But sometimes this list of vectors is redundant. We want to express these subspaces using the fewest vectors possible, and that's what bases are. So let H be a subspace of a vector space V. A set B1 through BP of vectors in V is a basis for our subspace H if the set of vectors is a linearly independent set and if H is spanned by those vectors. We won't go into too much detail now, but bases are going to be very important to us. They are essentially the building blocks of a subspace. We will be able to write any vector we want in our subspace as linear combinations of these basis vectors, and also it tells us how large a subspace is. So let's look at some examples and try to determine whether or not certain sets are bases for vector spaces. Our first example here, we have the vectors e1 equals 1, 0, 0, e2 equals 0, 1, 0, and e3 equals 0, 0, 1. Is this a basis for R3? We've learned previously that these vectors are called the standard basis vectors for R3. So you might expect that this set of vectors is a basis. Well, let's check. Are these vectors linearly independent? Well, if I make the augmented matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and I augment this with the zero vector, this matrix here is already row reduced, and I can see that my columns here, they are all pivot columns. So that tells me that the three vectors are linearly independent. Next, we want to check whether these three vectors span R3. There are two ways to think about this. One is, if I take an arbitrary element in R3, can I write it as a linear combination of E1, E2, and E3? So for example, if I have a vector V, let's just say that it has components A, B, and C. If I want to figure out how to write V as a linear combination of E1, E2, and E3, I can make an augmented matrix where I have E1, E2, and E3 augmented with V and try to solve the system. Right? But in this case, that's just 1, 0, 0, 0, 1, 0, 0, 0, 1 augmented with A, B, C. So we see that our solution is V equals A times E1 plus B times E2 plus C times E3. And this tells me that any vector in R3 can be written as a linear combination of A, B, and C. That's why the span of E1, E2, and E3 is equal to R3. Now when you're using this method of checking, you have this augmented matrix formed with your vectors augmented with an arbitrary element of your vector space. As long as this matrix is consistent, then the answer is yes. Another way to tell that the span of E1, E2, E3 is all of R3 is because R3 is a three-dimensional vector space. Now we know that the vectors E1, E2, and E3 are linearly independent, so their span is going to be a three-dimensional vector space. So since I'm spanning a three-dimensional vector space within R3, the span is going to fill up the entire space. So since the set E1, E2, and E3 satisfy the two conditions, they're linearly independent and they span our vector space, we say that it forms a basis for R3. Let's look at some more examples. So here we have the vectors v1 equals 1, 0, negative 1, v2 equals 0, 2, 1, and v3 equals 5, 6, negative 2. Is this set a basis for R3? Again, I want to check the two conditions. First, is it linearly independent? So again, I want to make the augmented matrix 1, 0, negative 1, 0, 2, 1, 5, 6, negative 2, augmented with the 0 vector. And I want to row reduce this. It reduces to 1, 0, 5, 0, 1, 3, 0, 0, 0, augmented with the 0 vector. Since this matrix is now in reduced row echelon form, I can tell that I have two pivot columns right here. This last column corresponds to a free variable because it doesn't have a leading entry in that column. So since I have a free variable, I have to conclude that the vectors v1, v2, v3 are not linearly independent. So this tells me that the set v1, v2, v3 is not a basis for R3. Let's look at a few more examples. In this next example, we have v1 equals 1, negative 1, 2, v2 equals 0, 1, negative 1, and v3 equals 0, 0, 1. And we want to know if this set of vectors is a basis for R3. So again, let's check our two conditions. First, is this set of vectors linearly independent? If we make the augmented matrix 1, negative 1, 2, 0, 1, negative 1, 0, 0, 1, augment that with the 0 vector, this row reduces to the identity matrix augmented with the 0 vector. So again, all three columns here are pivot columns. So that tells me that yes, these are linearly independent vectors. Next, we want to know if the span of v1, v2, v3 equal to R3. Again, one way to think about this is if I take an arbitrary element in R3, let's call it v equals a, b, c, can I write v as a linear combination of the vectors v1, v2, and v3? So to answer this, I want to solve the augmented matrix 1, negative 1, 2, 0, 1, negative 1, 0, 0, 1, and augment that with the vector v, a, b, c. Now when I row reduce this, I get 1, 0, 0, a, 0, 1, 0, a plus b, and then 0, 0, 1, negative a plus b plus c. Now the exact solution to this system doesn't really matter. What matters to me is that this matrix is consistent. Looking at the reduced row echelon form of this matrix, we can say yes, this is a consistent matrix, which tells me that yes, the span of v1, v2, v3 is all of R3. Again, another way to tell is by thinking about dimensions. Here, the vectors v1, v2, and v3 are linearly independent, so their span is a three-dimensional space. Now this is a three-dimensional space within R3, so the span has to fill up all of R3. So let's consider another example. So here we have v1 equals 1, 2, 3, and v2 equals 2, 5, 6. Again, let's try to determine whether or not these vectors are a basis for R3. So first, let's check that they're linearly independent. I can tell that they are linearly independent because they're not multiples of each other. So the answer is yes. So now we have to decide, is the span of v1 and v2 equal to R3? So let's first think about this in terms of the dimension. I have two linearly independent vectors here, so their span is a two-dimensional vector space. Now if I have a two-dimensional vector space within R3, well, that span isn't going to fill up the entire space, so there are vectors in there that can't be written as a linear combination of v1 and v2. So the answer here should be no. Let's confirm this using our other method. Let's take an arbitrary vector in R3. Let's call it v equals a, b, c. Now, can I write v as a linear combination of v1 and v2? In order to answer this question, I'm going to make an augmented matrix where I have v1, that's 1, 2, 3, then v2, 2, 5, 6, and I want to augment this with a, b, c. When I row reduce this, I get 1, 2a, 0, 1, negative 2a plus b, and then 0, 0, negative 3a plus c. I can tell that I have an inconsistent system here because this last row tells me that 0 equals negative 3a plus c. Since v was an arbitrary vector in R3, I can pick any value that I want for a, b, and c. So for example, if I pick a equals 0 and c equals 1, I see that this equation becomes 0 equals 1, which is false. So that tells me that I have an inconsistent system, which means that not every vector in R3 can be written as a linear combination of v1 and v2. So the span of v1 and v2 is not R3. Since one of the conditions is not met, we conclude that v1 and v2 is not a basis for R3. As we mentioned earlier, the span of v1 and v2 is a two-dimensional space because v1 and v2 are linearly independent. So you might ask, is v1 and v2 a basis for R2? So even though they're linearly independent and they span a two-dimensional space, these vectors don't belong in R2. If I take an arbitrary vector in R2, I can't write it as a linear combination of three-dimensional vectors. That's why the span of v1 and v2 is not R2. The span of v1 and v2 is a two-dimensional space within R3, and that's different than R2.